In this week, we are talking about the pre-processing techniques in the artificial intelligence, okay? To AI, and especially we are focusing on to the frequency domain, okay? Because you're in mechatronic engineering or the candidate of the mechatronic engineering, and so we need to debate how we can apply the some frequency filter or the signal processing on the artificial intelligence, okay? First of all, we need to talk about the Fourier transform. And also its series, okay? So, the Joseph Fourier in 1807 presented the fundamental theorem related to function representation, guys. Using the periodical function. Just like this one. He stated that the fx can be represented with the some bias value in terms of the a0 and also the infinite summation of the what, the cosinus and sinus, okay? This is the basic formula for the Fourier series, and so if we are utilizing this property, and then we can represent the whole function in terms of the what, the cosinus and sinus and the bias value, okay? Which means that we can divide or we can collect the whole the data in terms of the cosinus and sinus, and they have to the what, the frequency components of these properties, and so we can increase the R data set to apply this formula, okay? And so also the where the a0 can be represented with the what, 1 divided by 2 pi integral form of the 0 to 2 pi full period in here fx dx, okay? And also ak can be represented with the what, 1 divided by pi, the integral operator of the what, the 0 to 2 pi, and also fx times cos kx times dx. And also we can write to the what, the bk, 1 divided by pi, 0 to 2 pi, and also fx times sin kx dx. These are the coefficients of the what, of the R function representation, and also main formula can be given by using this one. And so any signal, any discontinuous or continuous thing can be modeled based on these properties which is given in the what, in this form. And so how we can utilize that? We can increase the R data set, increasing the properties of dataset using this feature. Just remember the previous lesson, we have talked about the what, the enrichment of the dataset in order to what, in order to stabilize the R training fast in the neural network structure. And so this can be built based on the what, based on this formation, okay? For example, the example can be given just like this one. If we have the any signal x and fx can be given in here, and so maybe we have a square signal in here, just like this one. This is not a differentiable function in here, but if you are using the Fourier series, and so the infinite sinus and cosinus can be created this signal based on the what, based on this formation. And so this is the summation of the what infinite sums of sinus plus cosinus. Okay? In Turkish, arkadaşlar bakın biz bu Fourier serisini kullanarak aslında ne yapabiliyoruz biliyor musunuz? Sonsuz sinüs ve kosinüsle bir tane kare dalgayı modelleyebiliyoruz. Bu da aslında bize ne veriyor? Eğer bizim elimizde bir tane sinyal varsa biz bu sinyalden aslında binlerce farklı bir sinyal formu burada bu formülasyona göre çıkarabiliyoruz. Bu bizim ne işimize yarıyor? Veri setini aslında genişletip bir sinyalin yerine mesela 10 sinyale çıkarabiliyoruz. Hatırlarsanız CNN'de biz ne yapıyorduk? Bir resmi 10 tane resme arttırabiliyorduk filtrelerle birlikte. Bu da aslında onun gibi ama tek boyutlu bir yöntem gibi düşünebilirsiniz bunu arkadaşlar. Asıl konu bu. Okay. Therefore, as we conclude, we can construct any signal using infinite sinus plus cosinus. Okay? And so this can be concluded that we can also separate the signal into the what? Into the frequency parts, okay? Which is enrichment, guys, okay? For example, if we have any ft signal in here, one bias value, and 1.2 sinus 2 pi 1 t, okay? Plus 2 times sinus 2 pi 2 t, and so this is the what? The 1 hertz. This is the 2 hertz. Maybe this is what can be called the new feature to our neural network. Okay? And so if we feed the only signal, one signal in here, and so we have the only one feature. But if we split the whole data set into the what? Into the components of the Fourier series, and so we have infinite number of the what? The different signal or the features into the what? Into the neural network. And so we can stabilize or converge to the what? The stability in training fast on the artificial intelligence applications. Okay? Any questions? Okay. So, in the second place, we need to talk about the Fourier transform, okay? This transform is utilized to what? Decomposing a function of time into what? Its frequency components. Okay? This is the reverse of the what, or the inverse of the Fourier series applications. Okay? In continuous form, we get the general formula, just like this one, xf, which is equals to the what? Minus infinity to infinity value, xt times e over minus j to ft dt. Okay? And so, these are the signal, and this is are the Fourier convolutional pattern. Okay, and also in discrete form we get, which is basically utilize the discrete form, because if we have any unknown signal or any signal, and so we may not have the specific formula like the sinus or cosinus or the square wave. Okay, and so in this case we need to utilize the discrete form, and which is given by with the what, the xk, which is equals to the what, this total summation operator of the what, the n equals 0, bigger n minus 1, x n times e minus j 2 pi divided by greater n times k. Okay, and so this is utilized for the what, the unknown pattern of any signal. But in this case we know xt signal can be analyzed. Okay, otherwise we cannot solve this integration technique in the what, in the continuous domain. Okay, but how we can apply or utilize the discrete form of this term? For example, in a matrix form, we get to the what, the x, the bigger x, w n times x. This is the input, this is the kernel for the what, for the Fourier. Okay, this is the frequency output. Okay, with x is equals to the what, x0, x1, x2, blah blah blah, x and minus 1. Okay, this is a time signal, but it's sampled. Okay, and so for example, if you want to create the Wn matrix in here, if we assign the smaller w in here, e minus 2 pi j divided by n, and so we can assign to the what, to this one. For example, the w matrix, this is the bigger w, which is equals to the what, w0, 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 and so also w0, w0, w0. This is the what, w1, w2 and w3. Just remember the DSP lesson. If we are increasing the overfactoring here, and so we can differentiate what the different frequency pattern in here, w2, w4 and w6 and w3 and w6 and w9. Okay. If you are using the Euler identity formula, we can write this matrix just like this one, 1, 1, 1 and 1. Okay, 1 minus I minus 1 I. Okay, and also 1 minus 1, 1 minus 1, and also 1 minus I, sorry, minus I minus 1 I. Okay, and also this must be written just like this one. Okay, so these are the what, the Fourier matrix. And so how we can utilize these forms? In this form we can apply the what, the whole signals into the what, into the this one, and so we can generate what, the different frequency pattern of the what, R signal. For example, we are using or feeding the total X signal, and also we can build the XF signal in here, and then we can train the R neural network based on this information for a given Y target. And so this is the enrichment of dataset, and maybe the R dataset can be more observable or the discriminative in the in the frequency domain, but the not time domain one. Okay. This is why we need to utilize the Fourier transform or the Fourier series on the on the artificial intelligence pre-processing phase on the data set, guys. Okay. Any question? Okay. If you don't have any questions, and so here's the wavelet transform is the another topic of the R lesson. The Fourier transform has basic disadvantage, guys. For example, the temporal information does not track in Fourier transform because we apply the signal to the Fourier transform, okay? We cannot search the temporal information of the R algorithm, and also it is entirely depending on one basis function, okay, which is equals to the minus a j 2 pi f t, okay. This is the convolution, and this is the Euler identity formula for the for creating the frequency pattern of these terms, okay. For example, if we apply the Fourier transform to the xt signal in here, just like this one, and so we will obtain this the f and this the magnitude, okay, and ft is applied in here, and so this could be generated with the with the 20 Hertz, for example, which is the 100 Hertz, and this gives us the 150 Hertz, okay. And so we have only 3 property of description in a signal, okay. This is the basic Fourier transform formula. This Fourier transform is applied on the total signal, and it generates to the different frequency pattern, but we don't know which area is equals to the 20 Hertz or which area is equals to the 100 Hertz, okay. This is the Fourier transform. On the other hand, short time Fourier transform gives us to this is t, this is xt, okay. And we can build any random signal in here just like this one, and also in the short Fourier transform we define a window S1, S2, and S3, and S4, okay. And so, in this case, we can generate to the what, maybe the frequency pattern, the magnitude and the F can be built with the what, with the slowest frequency. And also, this generates to the what, just like this one, this is the mag, and so maybe this one. And also, this is the higher frequency range in here, the F and mag, and also this creates the what, the higher frequency. And also, maybe this is the general pattern for the what, the F and mag, and maybe this is the what, the spread, the whole the region of the frequency components in here. Okay. So, if we have the XT signal, we can fed it, but this is the maybe as X1, X2, and X3, and X4. This can be fed into the neural network in order to what? In order to enrich the what? The whole the data set in here. And so, this could be generated to the what? The Y in a stable range. Okay? So, if we want to stabilize the hard training path, and so we can apply the what, the pre-processing in terms of the what, the Fourier transform, short Fourier transform, or the Fourier series analysis. But we have some important formula for the what, for this temporal feature of the frequency patterns. In the short time Fourier transform, we apply the regional Fourier transform at each specific point or the region. Okay, and so how we can obtain at the same time the time and the regional properties of the instantaneous frequency. And so the solution is the wavelet transform. But in order to understand the wavelet transform, we will look at uncertainty principle, which is stated in the Heisenberg. Okay, and so what is the Heisenberg said? If we have any diagrams in here, just like this one, speed of particle, which is given in here, and also position of the particle, which is given here. And so maybe we have a speed in here, just like this one, and also maybe we have a position in here. Okay. And so the basic guess is to what is particle is at this point with the speed and the positions. Okay, and so the Heisenberg states that if we have this property, and so we can draw to the what, to this one, we cannot measure at the same time the speed and the position in the what, in the physical world. Okay, and so this is the resolution of measurement, guys. Okay, either we can select this one or this one, but if we want to describe the certainty in here, and so if we increase the position error, and so we have specific at the what, the speed, or if we want to specific position, and so we can spread the speed in here, or the error tolerance is increased, right? Just like this one. And so this is very certain at the speed, but at the same time this is very uncertain. Okay, at the same time this is very certain for a speed, or no, for a position, and so this is very certain for speed in this case, and so uncertainty position which is given here, and also we can define to the what to this one, very uncertain at speed. Okay, and so this is the what Heisenberg principle for to what the measuring the speed and the position of a particle at the same time. Okay, but this analogy is current or the same for the what for the signals, guys. Okay, so in this case we can define to the what to this uncertainty based on the what, based on the time and the frequency. This is the same pattern. Okay, and also at the same time we have a specific frequency or we have a specific time in here. Okay, and then this is the exact position of these terms, but just like in the what in the Heisenberg principle, this is the measurement resolution. And also if we have this property, and also if we want to have the what the higher frequency resolution, and so this is very certain, but in time we don't know. Okay, just like this one, if we want to obtain the time precisely, and so this is very certain. Okay, but otherwise we need to what to split the whole energy into the what either the time or the frequency. In conclusion, we can say that at the same time we cannot obtain to the what the exact frequency, instantaneous frequency for a given time with a precise measurements. Okay, either we can measure the frequency or the time. Okay, so if this is the case, and then we can deduce that so this resolution must be changed in time, which means that in the Fourier transform we have the f, and this is the what, this is the power. Okay, and also this is the what the FFT signal, this is the f1 and f2, this is FFT, fast Fourier transform, for example. In the other place we need to draw this line, the time and the frequency in here, not the body diagram. Okay, and so we can split the whole region just like in the Heisenberg principles. Okay, at the same time we want to define the frequency and the time, and so in each case we divide the whole area. Okay, this is the measurement range or the resolution points. Okay, so in this case this is the what, for example, this one, and so this may be 2 and 3. Oh, this is the window, guys. Okay, and if this is the window, and so we can search the whole frequency pattern in this window. This is the short time Fourier transform. Okay, but if we want to obtain the instantaneous frequency for a given time, we need to state that this area can be changeable. Okay, which is called the wavelet transform, guys. Okay? And so, in the wavelet transform, we can write that it captures wavelet transform the instantaneous frequency characteristics instead of regional or total frequency one. Okay? So, we define the same way with the what? The short Fourier transform, and also we need to define the geometrical representation of the wavelet one in here. Okay? So, this is the short Fourier transform. Each area must divide into equal points based on the what? The windows. Okay? This is equal space. STFT. Okay? But in the wavelet transform, we draw this line just like this one. We split again to the what? The whole area. But in the first place, in the level 1, we divide it by the 4 parts. This is the L1, level 1. But in the second part, we divide 2 times more than the first one. Just like this one, L2. And in the second one, we divide it by the multiplication of the 2 of the L2. Okay? Just like this one. And so, in each case, just see that we divided by the 2 times more than before. Okay? And so, this creates the what? The different spaces. Okay? And also different levels in here, which is called the what? The wavelet. At the same time, we catch the instantaneous frequency of the what? For a given signal. But in this time, we don't have such kind of properties of this term sky. Okay? So, the general formula can be given by with the what? With this one. We have the A and B scale and shift factor in here, just like this one. 1 divided by square root A and times minus infinity to infinity values, and also we have some basis function xb divided by A times fx times dx. Okay, this is the convolutional conjugate, and so this is defined the convolutional canal. Okay, okay, and also in the matrix form we get the same pattern, Wn times x. Okay, it's the same analogy, but the Wn is created. For example, the Haar filter. Okay, in the Haar filter, Wh, which is defined with the what? 1 and 1, 1 and minus 1. Okay, these are regional patterns. But how we can analyze these features? We need to show this filter in an examples. This is the what? The Haar filter. 1, 1, 1, minus 1. Okay, and so how we can apply this filter? In this case, we built to the what? To the 2 graph in here, just like this one. For example, the T an XT signal which is given in here, and also we have a random signal in here. And then what? If we apply the Haar filter, this simple convolution, right? And so in the Haar 1, we apply to the 1 to minus 1 to the 1. This is 1 and this is minus 1 and goes on this structure. And so this convolve the whole signal. But in the second level, just like before, and so H2 is the what? Is the 2 times smaller than this one, 1 and minus 1. But for example, this point is 2 and this is the 1 and this is the 0, 1, which means that we divide the whole convolutional pattern into the 2, and so maybe this can catch the 2 Hz signal, but this maybe catch the 4 Hz signal in here, just like this one. Okay. If the frequency increases, then we can obtain regional pattern in here at the different form of these terms. Okay? So, in Turkish. Şimdi arkadaşlar bakın, bu wavelet transformda bizim yaptığımız şey aslında ne biliyor musunuz? Fourier transformun 2 tane aslında artefaktı var. Yani aslında bozukluğu var. Birincisi, bu aradaki aslında değerleri, yani regional olarak size herhangi bir bilgi veremiyor arkadaşlar. Ve bir tane aslında fonksiyona bağlı olarak kalıyor. Ama bakın şimdi sizin şöyle bir sinyaliniz varsa, bu sinyalin içerisinde mesela şu bölgenin içerisinde, mouse'umla gösteriyorum ya, şu bölgenin içerisinde şöyle hangi frekans aralığı var biz bunu bilemiyoruz. Bunu yapmak için ne yapmamız lazım? Adamlar bir tane daha yöntem uydurmuşlar. Bu yöntem short time Fourier transform. Belli pencereler tanımlıyorlar, window'lar tanımlıyor. S1, S2, S3, S4. Bunların hepsine sıra sıra Fourier transform uyguluyorlar. Bunları uyguladıktan sonra hepsi farklı bölgelerde frekans veriyor. Ama bakın bu da yetmez. Neden? Çünkü bu regional. Yani siz buraya baktınız, sonra buraya baktınız ama arasında ne olduğunu bilmiyorsunuz. Yani aslında zamana yayılmıyor bu. Şimdi bunu yayabilmek için bizim ne yapmamız lazım? Heisenberg'in belirsizlik ilkesi var. Belirsizlik ilkesi ne diyordu? Bizim bir pozisyonumuz var, bir de hızımız var. Biz bunun ikisini de aynı anda ölçemiyoruz. Yani siz pozisyonu hassas ölçecekseniz hızı düşürmelisiniz. Hızı ölçecekseniz pozisyonun hassasiyetini düşürmelisiniz. Aynı şey arkadaşlar sinyallerde de var. Eğer ki bir sinyali tamamen zamanını ölçmek istiyorsanız bunun frekansını düşüreceksiniz, hassasiyetini. Ama bir şeyin frekansını daha iyi ölçmek istiyorsanız bunun zaman hassasiyetini düşünürsünüz. Wavelet transform da aslında bunu yapıyor. Şimdi bakın bunu nasıl yapıyor? Bizim burada Fourier transformun içerisinde bir tane sinyale verdiğimizde bütün sinyalin hepsini bir tane frekans alanına çeviriyor. Burada F1 ve F2 anlamlı bilgi. Ama bu bize yetmez. Çünkü bölgesel bir bilgi vermiyor. Short time Fourier transformda ne yapıyor? Belli bölgelere böldüğümüz için frekansla time'ın arasında istediğimiz bölgede işlem yapıyoruz. Ama bakın bu bölgelerin hepsi eşit alanlı. Eşit alanlı olduğu için de ben ne yapıyorum? Diyorum ki bu sefer git en alt bölgeyi 4'e böl, üstünü 8, 16, 32'ye böl. Ve hangi frekans varsa burada, mesela atıyorum çok yüksek bir frekans var, bu bölgede çıkıyor. Düşük bir frekans var, L1 bölgesine çıkıyor. Eğer ki yüksek varsa mesela ya da arada bir sinyal varsa L3 bölgesine çıkıyor. Yani sizin bu sinyalleriniz neyse burada aslında hepsini tek tek alabiliyorsunuz. Ve bunu nasıl yapıyorsunuz? Bir tane convolutional kernel tanımlıyorsunuz burada. Zaten biz ne diyorduk? Fourier transformun içerisindeki bütün kalıpların hepsi nedir? Aslında bir konvolüsyondur. Konvolüsyonu siz buraya aldığınızda, bir sinyalle çarptığınızda bu kalıbın sonucunda alan formunda size bir bilgi veriliyor. Frekansı zaten biz böyle çeviriyorduk. O zaman ben de diyorum ki burada bizim özel filtrelerimiz olsun. Bu filtreleri gidelim biz tanımlayalım bu şekilde. Ve bu filtrelerin hepsini mesela 2 Hz'lik bir filtre tanımının bunu yarıya bölersem 4 Hz'i algılıyorum. Yarıya bölersem 8 Hz, yarıya bölersem 16 Hz ve ben matrise çarptığımda benim frekansım neyse size tamamen onları veriyor arkadaşlar. Yani konunun en temel özeti bu. Şimdi bakın bir sonraki ders ki ona 7'de başlarız. 7'de başladığımızda bunun Python'da örneklerini yapacağız arkadaşlar. Bütün hepsinin ben Python'da kütüphanelerini size yazacağım ve bir tane gerçek sinyal üzerinde bunları biz nasıl değerlendiriyoruz, bunun veri setini nasıl arttırıyoruz, aslında size bunu göstermeye çalışacağım. Herhangi bir sorunuz var mı? Any question? Okay.